It's welcome to the MCube weekly seminar. Today we have Manda Chasteen, postdoctoral fellow here at MCubed. Manda received her PhD from the School of Meteorology at the University of Oklahoma in 2021. She also has a MS from the same place and a BS in atmospheric sciences from the University of Illinois. Research and expertise and interests are in mesoscale meteorology, severe convective storms, atmospheric dynamics, numerical weather prediction. She's particularly interested in understanding the multiscale processes that interactions and convective environment feedbacks that occur in high-impact severe weather events. And today the title is a multiscale investigation of the 26-27 April 2011 tornado outbreak. And Manda, the floor is yours.
Okay, thank you for that introduction, Rich. Can everyone hear me okay? Cool. Yeah, so today I'll be talking actually about my PhD work that I did at the University of Oklahoma. So it's been a year and a half now, so it's kind of like refreshing to look at this stuff because I haven't really talked about it in a long time. But I've recently started working with Rich, trying to simulate in an idealized setting some aspects of this case. So there will be some new stuff in here too. So just some background. So this outbreak was the most prolific and destructive portion of a multi-day outbreak that actually spanned the 25th through the 28th. And during this full outbreak, there were multiple episodes of convection that produced 343 confirmed tornadoes and 321 fatalities and more than $11 billion in damages. So you can see down here is the storm reports for each of these days. But I'll just be focusing on this portion from the 26th through basically early on the 28th. So this will include the prolific supercell tornado outbreak that most people are familiar with. But that was actually preceded by two quasi-linear convective systems, the first of which was actually anomalously severe for QLCS, and there were 5 EF3 tornadoes produced by that system. And then there was a second system. It wasn't prolifically tornadic, but as I show in some of my work, this had dynamical effects that kind of spanned, or I guess expanded into the larger scale that had some implications for the supercell outbreak. So just to show you sort of the morphological evolution, now we have, what's showing in the animation is the development of the first QLCS. And this was primarily a nocturnal system that moved through the southeast overnight. Here is the second QLCS that developed over Arkansas. Oh, I guess, can you see my, okay. Yeah, and so here's the supercell outbreak that developed on the afternoon and evening of the 27th. So that was the outbreak, or at least what I'm focused on, is primarily, the severe reports were primarily in the southeast, but also in the southern Great Plains. So some broader motivation. So forecasting the development, morphology, and severity of convection in the southeast is notoriously challenging. And this is for a variety of reasons. One of which, I guess, is that severe events are often associated with slowly moving, highly amplified synoptic patterns and multiple interacting jet streaks. But in these cases, you may have multiple episodes of convection. So you have these mesoscale effects or also these upscale feedbacks in all this stuff tied to the latent heating that adds to additional complications with forecasting. But typically in the southeast, I guess what you most often hear about, at least these days with research, are these high shear, low cape regimes. So in that case, your conditional or limiting factor would be the cape. And so since that's integrated, that could be sensitive to all kinds of model errors. The case that I'll be talking about isn't really in that regime, but that's really where a lot of the focus has been. But you can see, I guess, on the right here, this is a great example of how the mesoscale environment is often highly heterogeneous and also rapidly evolving. So you tend to, have these really small corridors or maybe higher cape or higher shear profile or stronger shear profiles that you end up getting more severe weather than you anticipated. And these things are hard to, I guess, depict in advance. So. Another reason is that the convective organization is often highly complex and poorly depicted by numerical weather prediction. And so for one example, you often have quasi-linear convective systems or mixed mode convective systems, or however you want to call that. But in that case, you basically are conducive to multiple overlapping hazards. Sometimes you get convection that develops out in the warm sector, though, so that would be away from any discernible surface boundaries. So you may see these cases where they talk about, some very subtle confluence line, or they don't even see a feature at the surface that's responsible for that. And in that case, this convection tends to be more discrete and therefore more severe. So if you read the outlook discussions in a lot of these events, one thing they really kind of stress in terms of the upper end of the severity is whether or not convection will develop in the warm sector. Because in that case, you may have supercells versus a squall line or something along a front farther to the west. So the mesoscale processes responsible for the initiation and organization of this convection are poorly understood. They're difficult to detect with a conventional observing network. And also just even having special observations, there's a lot of mesoscale heterogeneity and a lot of mesoscale variations there. So it's hard to really know what you're seeing too without a lot of observations. But there are also complex interactions that may occur between convection and external processes. And by that, I mean processes on a variety of scales that would influence the convective morphology. So I'll just kind of really start out by going into the outbreak chronology. So I have published 2 papers on this event, the first of which discusses the chronology. The second of which I won't have a lot of time to really get into today, but I will touch on aspects of that. And that is how the environment was modified due to the quasi-linear convective systems. And so a lot of things that are going on in this case I found to be attributable to these sort of upscale feedbacks where you get basically an upscale dynamical response to a mesoscale or large area of latent heat release. And because of that, you have a lot of flow imbalance and you have a lot of rapid adjustments and thus a really strong ageostrophic motions. So I'll just kind of touch on that, but if you're interested in that aspect of that, I encourage you to look at my paper or come talk to me after. So just to kind of get started with the synoptic overview. So for the entire outbreak, like I said, span the 25th through the 28th. This was supported ahead of a slowly moving long wave trough that amplified with time over the Rocky Mountains. And so if you look back upstream, you can see that this trough actually stemmed from an upstream anticyclonic Rossby wave breaking event and a polar subtropical jet superposition. So it's been a while, but I know Andrew Winters, right before COVID, gave a seminar on these superpositions and how they tend to be associated with these high impact weather events. So I did find that was the case in this event. The trough base persisted over the south central U.S. for multiple days. And this favorable positioning this was favorable positioning with respect to the topographic variations, so such as the Gulf of Mexico or the soil moisture, if you were at Carrie's seminar, but also the elevated terrain to the west. And so basically, because of this, you had repeated, formation of a Lee trough and dry line, Lee cyclogenesis, and the replenishment of potential instability, just because you're so close to those sources. And also, so throughout this period, though, there were a series of shortwave troughs that were embedded within this broader upper-level jet that moved into the lee of the Rockies. And so each of these, and there are 3 that I will be talking about, promoted cyclogenesis and episodic convective development throughout this period. So the main jet streak that I'll be talking about in this case, I label as Jet 1, so J1. And that's sort of this main slowly moving jet streak that comes in. And so within this broader system, as that jet rounds the base of the long wave trough, you have 3 short wave troughs. So I label as SW1, SW2, and SW3. So this is sort of the surface depiction of how this evolved. So you can see on the 25th, SW1, so shortwave 1, moved into the southern Great Plains and promoted cyclogenesis along this quasi-stationary front in the formation of an expansive QLCS. I'm not talking about this QLCS other than just highlighting that it formed in this case. But this shortwave amplified over time. You get the development of this low, which I've labeled L1, and that actually moves into the upper Midwest and occludes. But this promoted the eastward expansion of an upper level trough in the formation of a PV hook. And subsequently, the upper level ridge downstream amplified over the eastern US, and the warm sector expanded polarward. So following this, the second shortwave, so this is the first shortwave that I'm really going to be concerned with because this was responsible for the development of the first QLCS. So this moved into the southern Great Plains on the afternoon of the 26th. So this basically restored lead troughing and cyclogenesis over the southern Great Plains, thus supporting air mass recovery and the formation of that first QLCS on the evening of the 26th. But as you can see, is this shortwave actually amplified with time, basically on the backside of that QLCS, is that grew upscale. And this promoted cyclogenesis, which I've labeled here as L1, over the Midwest behind QLCS. So this is on the morning of the 27th. And I'm not going to show this in this talk, but I have run simulations with them without latent heat release, and I found that this low does not actually develop without latent heat release. So this was directly tied to that system in the baroclinic interactions between the latent heat release and the broader synoptic environment that promoted that low. So by the time you have basically the main outbreak that people are concerned with here, you have these two low pressure centers, so L3, which starts to develop as the main shortwave, or SW3, moves into the southern Great Plains. And then you have, so that low and then this other low that are actually only located, say, around 1,000 kilometers from each other. So you have two sort of synoptic scale low pressure systems in this case that are relevant during the main supercell outbreak. But concurrently, after the development of these QLCSs, you get an upper level ridge amplification that actually happened really rapidly and was associated with the development of this one jet streak J2 that rapidly surged northward. And that's something that I saw early on when I was looking at this case, and that's really what kind of led me to look into these upscale feedbacks, was because that was such a rapidly evolving jet streak, and basically the entire synoptic environment changed within the period of, say, 6 to 9 hours. So there was also, like I said, the third shortwave that moved through, promoted the main low that was relevant during the afternoon of the supercell outbreak, and supported the formation of the second QLCS and the supercell outbreak. But so during the afternoon, when the supercell outbreak is occurring, you end up with this coupled upper level jet configuration that was associated with the main jet J1 that moved into the base of that long wave trough, and this unbalanced jet streak J4 that developed basically to the north of the second QLCS. And so that dynamical evolution led to rapid strengthening of the low-level jet and the low-level shear over the warm sector. So I'll show that a little bit more here. So here's kind of on the left, the upper level evolution, on the right, the low level flow evolution, starting on the evening of the 26th and going through basically the evening of the 27th. So here's J2 that develops rapidly to the north of the first QLCS right after it develops on the evening of the 26th. And this jet attained wind speeds greater than 140 knots by 3Z. So that's a period of 6 hours after that convection started to develop. And as that moved northward and strengthened, the low-level jet consequently strengthened by 20 to 25 knots ahead of that system. And by 9Z, so this is when that first QLCS is mature and has grown upscale, you have 60 to 70 knots extending into the Ohio Valley. So that's basically strengthening the winds over the warm sector, but also expanding the warm sector northward ahead of that system. So you're also strengthening the shear ahead of that system. And so then following the development of the second QLCS, you have this jet J4 here that develops over the Midwest after 9Z and also rapidly strengthens to greater than 140 knots by 18Z. And so then you have this second period of rapid low-level jet intensification accompanying the formation of that jet streak. And this is all occurring in association with these convective systems, but is also then adding to the effect of the main synoptic system that's coming in from the west. So these are, I would not say the only contributing factors here to the strong shear that you see, but these are certainly playing a big role and affecting the basically the environment over the southeast prior to the arrival of the main shortwave and the main forcing. So just sort of to summarize here, here I'm depicting the three shortwaves and then these QLCSs, and then following that, the movement of this third shortwave, which was associated with the deep tropopause fold into the southeast, or I guess really into the Mississippi Valley in advance of the supercell outbreak. So a little bit more on the pre-convective environment. So I'll just go through the three systems individually, but so this is on the evening, or I guess late afternoon of the 26th. And so you can see here, this is what the environment looked like over the southern Great Plains. You have this Lee cyclone here. This actually persisted through this period. So this was actually, I think, more tied to the broader jet streak that's upstream. This feature persisting here, though, prevented any cold air mass from surging into the southern Great Plains and cutting off the outbreak prematurely. So you have this second area of development down here, and then you end up with convection initiation ahead of this short wave as this moves into the southern Great Plains and into the lee of the Rockies. And so over time, here's sort of the cape and shear evolution ahead of this system. You can see that the cape decreased throughout the environment after sunset, but remained highest ahead of the southernmost bowing segment of that system, which was the main region of severe weather and where the strong tornadoes occurred as it moved through the southeast. And this was also supported by strong deep layer shear and also low level shear that rapidly strengthened throughout the inflow environment following convection initiation. So you can see here that here's the shear over the lowest 1 kilometer as depicted by the RUC model. Sorry, I didn't clarify that earlier. So these are a series of 1 hour forecasts from the RUC. So you can kind of think of it as the hourly analyses, but slightly different. But you can see that the shear during the evening was 15 to 30 knots over the southern Great Plains, and by 3Z, so there's 6 hours, it has strengthened to greater than 40 knots, with areas even greater than that. So one thing that I hypothesized, I guess, due to these rapid environmental modifications due to the system is that the shear enhancement was the direct result of these modifications produced by the QLCS, such that it actually increased its own severity. And I won't go into that here too much, but I encourage you to look at my part 2 paper if you want to know how that ended. But ultimately, I think I showed convincingly that is probably what happened. But by 9Z, you can see that you have incredibly strong vertical shear over the lowest 1 to 3 kilometers. And your shear vectors in this case are actually oriented largely parallel to the system. So this yields a strong or large streamwise vorticity for low-level inflow. So this is in contrast to a lot of traditional idealized sort of frameworks that we have of MCSs and bow echo dynamics by Morris and others that have only included the shear perpendicular to the line. So one thing that I kind of motivated, or I guess said in my papers based on this finding is that we need to start kind of examining how these structures evolve in idealized frameworks that actually have really strong line parallel shear as well. And since then, I know some people, for example, Matt Brown at NSSL have actually begun to look into that. So I'm really happy to see that. But I think that's a pretty typical thing that you see in the southeast or in these synoptically forced systems where you do have a really strong low-level jet and you end up with a QLCS. So just to talk about the second system here, this system wasn't prolifically severe, so in that sense it wasn't that interesting, but it was interesting in terms of the environmental modifications that it produced. But this system formed actually ahead of the main shortwave SW3 that was also responsible for the development of the supercell outbreak. And that system moved into the southern Great Plains. You end up having destabilization, air mass recovery in the wake of the QLCS, or the first one. And you typically, or primarily got elevated convection that actually developed to the north of this outflow boundary that was produced by the first QLCS, but also ahead of a cold front aloft. And the cold front aloft is something I will be talking a bit more about. But you can see that structure here in the top right where you have, this plot is showing equivalent potential temperature. The solid contours are potential temperature. And this is basically a cross-section that's going from the Red River down into Louisiana. So across the region, that part of the system developed. And you can see that you have this basically nose of lower theta E air, but also cooler air that's moving as this air mass moves downslope and subsides, moves over the warm sector. So I tied parts of that development to this evolution, but I will say the evolution of this system and basically its entire morphology, the timing, location of its initiation, and so forth were all poorly depicted by numerical weather prediction. And I have yet to see a simulation that actually depicted the system correctly. And so in real time, this is actually a major source of uncertainty for forecasters because it was basically limiting, I guess, the northward extent of the warm sector during the supercell outbreak. So this was a major forecast challenge. And I think that there are probably a number of reasons why it was so poorly depicted, but one would be the dependence on the first system. So a lot of simulations I've also seen have not depicted the southern end of this QLCS correctly, or they have this dying out while the rest of it persists. And you can see that a lot of this convection actually formed in the north of that outflow boundary, so that cold pool would be relevant to its development. But another thing, I guess, talking about the upper level jet modifications that came or arose from this system, you also have modifications to the main jet J1 that's moving into the southern Great Plains at this time. And in my part 2 paper, I show that the development of this system actually occurred in the exit region of that jet, and as a consequence, actually kind of split the exit region of that jet into 2 branches. And it was the southern branch that was diverted over the southeast, and that was then relevant for the supercell outbreak. And so as a consequence, your shear actually strengthened a bit to the south of that system, but you also have shear vectors that are now more veered. And you can kind of imagine what would happen if you didn't have this splitting effect occur, is that you may have, I guess, a greater southerly component of your deep layer shear vectors, so possibly would have maybe favored more of a squall line later on than discrete convection. But you also had the low-level jet strengthening rapidly as the system developed too, and you can see that in these photographs here. They may be kind of hard to see, but the red and orange colors are the low-level winds, and so you can see that the low-level jet and the low-level shear actually strengthens over the warm sector before the deep layer shear does, and that primarily occurs as this main jet streak moves into the region, so during the late morning of the 27th. So to get into the part that everyone really cares about is really the supercell outbreak. So I think one thing, or at least something that I thought in my mind, thinking about these prolific tornado outbreaks, is that you have like a rapid cyclogenesis event or something like that. That is absolutely not what I found occurred in this case. And so what I found is basically you have your warm sector here, which is recovering in the wake of these QLCSs, and this is where convection ultimately develops. You do have this low, but this low does not deepen very much, and it also doesn't move very quickly. And so you neither have a highly diffluent shortwave trough nor rapid surface cyclogenesis during this event, even though you have a turbopause fold that's extending down to, say, around 700 millibars. So despite the strong dynamics, it isn't some rapid response to that I'm seeing, where these really strong ageostrophic motions, but rather I see that the strong low-level jet and the strong low-level shear present over the region was largely attributable to the accumulated flow modifications from the QLCSs and the upscale effects from those. So these are then compounding on the effect of this main shortwave as it moves through, but like I said, you don't have rapid surface cyclogenesis, and you end up with these sort of sub-synoptic scale lows, and there's the other one that formed behind the first QLCS that's located a little bit farther north. And these sort of, I guess, smaller scale systems, I guess, could be contrasted to, say, the 1974 super outbreak, where you had a much more broad warm sector. But so during the afternoon in the southeast, so right ahead of the supercell outbreak as it's starting to develop, you have remarkably high cape and steep mid-level lapse rates, and also strong vertical wind shear. So this is basically putting you in the extreme end of the parameter space for significant tornado environments. But you can also see that these soundings have an interesting character to them. So the sounding in slide L was taken where this pink star is located here. So you can see that it was released roughly around this time, so through these low-level cloud bands. And the structure that you see is the boundary layer, which is shallow, which is topped by this moist, absolutely unstable layer, which is capped. You have this secondary sort of low-level dry layer, and then this inversion, but then you also have the main elevated mixed layer on top of that. And you can also see the Jackson sounding looks somewhat similar to the slide L sounding, but it looks like it's been lifted a bit. And also the Birmingham sounding, which is quite a bit different. A lot of people talk about this sounding when they talk about this event. This sounding was actually released here. So it's kind of at the leading edge of where these cloud bands start to develop. And these cloud bands are really what I'm going to be talking about when it comes down to what actually evolved into the supercells, or where did convection initiation occurred in this case. But this structure has somewhat resemblant of a MAUL. I have an asterisk next to it because it's not fully saturated. You can see the boundary layer is actually quite a bit deeper. It's warmer out there. You don't have a lot of cloud cover, but you have this really pronounced mid-level inversion in an elevated mixed layer on top of that. So despite that there's negligible sin, if you actually just calculate this, which probably due to the virtual temperature correction, which is something that Rich and I have talked quite a bit about lately, is if you look at the soundings and you don't see sin, it's probably because of, the virtual temperature correction is, the line is a little bit farther to the right. But anyways, despite negligible sin, mid-level cooling was likely a necessary prerequisite for convection initiation. So partial theory isn't the whole story in these cases. So what I ended up seeing is, or what ended up happening was that numerous long-lived tornadic supercells developed along mesoscale bands and moved throughout the warm sector. And convection initiation occurred primarily, but not exclusively, along two distinct bands. So the first band would be what I'm showing here, and the second band is this sort of arc-shaped band that you can see developing to the east of that one. Like I said, not exclusively. There were a couple cells that formed not along these bands as I see them, but there's a lot going on here. You can see there's all kinds of cloud bands, all kinds of scales. Over here you have, sort of a developing cumulus field, and these are where the cells ultimately develop. But ahead of that, there's all kinds of stuff going on. But these supercells ultimately remain discrete for several hours prior to growing upscale into a QLCS. And so the mesoscale environment and the initiation pattern both were favorable for limited storm interactions in this case. And so ultimately, it was the unique overlap of buoyancy, highly favorable vertical shear profiles, and the mesoscale organization that primarily developed along these two bands, but remained discrete for several hours. That contributed to the prolific nature of the supercell outbreak. So the western band of supercells I found developed ahead of a diurnally modified cold front. This would be a diurnally modified Pacific cold front that actually acquired the character of a dry line following the onset of solar heating. So basically you got a lot of mixing, heating, and it's really mixing down this really dry air. So if you look at the dew points behind this, they were very low. And the dominant warm sector band of supercells I found developed ahead of a cold frontal loft, the same cold frontal loft I mentioned earlier that was responsible for the development of the second QLCS, or at least part of it. And this cold frontal loft originated as subsiding post-frontal air, so actually pretty low level. You can see that as it moves over the warm sector, it's centered around, say, 800 to 750 millibars. But as this, basically a surface-based front or near surface-based front over the elevated terrain, came down slope and overran the potentially cooler moist layer from the Gulf of Mexico. So I think the main thing that I really got from this is if you were just looking at your conventional pressure levels, so 850, 700 millibars, 500 millibars, you're not going to see these sort of structures, at least in this case that it's sort of a low-level intrusion of drier, cooler air that moves over the warm sector. You really do have to look at a cross-section to see these. So I think that's one complicating factor for forecasters is that if you're not looking at, a cross-section, you're often, you're apt to miss these things. So here I'm showing on the top left is a 3-hour theta E change, 800 millibars. So this is around the level that the cold frontal loft was centered at as it moved over the warm sector. And here are high split trajectories from 4 locations. These were taken at approximately the same latitude, so around the latitude of Jackson, Mississippi. So Monroe, Louisiana is the one on the top left, and that's the farthest to the west. And then on the bottom right is Montgomery, Alabama. So that would be the farthest to the east. And so Monroe, Louisiana, you can see is actually behind the cold frontal loft, but you also just have a deep tropopause fold, and you also have a really strong just sort of dry conveyor belt that's really descending. So over 24 hours, you can see that this air is actually descended almost 7 kilometers in some instances. And you also have some semblance of moist air near the surface still, but you are getting a lot of mixing behind that. But what's really interesting in these, I think, is comparing the Jackson, Mississippi and Meridian, Mississippi profiles. So Meridian, Mississippi is actually just located out in the warm sector, so ahead of the cold frontal loft and ahead of the dry line. And you can see that consistent with what you would expect with a veering wind profile, you can kind of get this from these trajectories and how they evolve. But you have this warm, moist air at low levels that comes from the Gulf of Mexico. Above that, you actually have this warm, drier air that's coming from the western Gulf of Mexico. And if you remember when I showed the Slidell sounding, I noted there was like a dual inversion structure. And this is, I think, that source of that air mass. And this is descending, I think, over the higher terrain in Mexico, but kind of just persisting over the Gulf for a while, being stirred around. But it's actually at pretty low levels, but not near the surface. So but probably within the lowest kilometer or so. And that gets evected into the southeast. But then above that, you can see that you have generally just air from the Mexican plateau and some descending air. So that's leading to your elevated mixed layer. However, if you look behind the cold frontal loft, in the Jackson profile, you can see that you have this same structure, but you also have this third sort of, or fourth airstream here. And this is cool, dry air that descended from the upper troposphere over West Texas during the previous evening. And that flowed largely laterally into the southeast. And so that air was cooler or potentially cooler than the air from the elevated mixed layer, but it's warmer than this air from near the Gulf of Mexico. So you have this sort of sandwich-like structure. And that's where these air streams are coming from. So during the supercell outbreak, I found that the deep layer shear vectors were oriented favorably for the formation and sustenance of discrete supercells ahead of both the dry line and the warm sector bands. The angles here I found were about 35 to 45 degrees. So if you go back to Morris's paper forever ago, looking at the angles of the shear vector, the deep layer shear vector relative to the initiating boundary, you find that these angles are favorable for a right-moving supercell persisting. You don't have a lot of cell splitting or a lot of interactions through that process. So it's really favorable, I guess, for just sustaining discrete convection, all else being equal. But I also found that the notably high SRH values over the southeast, which it's hard to kind of see probably here, but even over the warm sector, so where you have this highest values, this is in remnant or recovering outflow, but even just farther over the warm sector, your SRH values were upwards or greater than 300 meters squared per second squared over the lowest 1 kilometer, which is pretty insane. But I found that these values were a combination of large streamwise vorticity, but also strong store of relative winds in the lower troposphere that were oriented at a large angle to the low-level jet. So that basically yielded really strong. I guess your storm relative winds and your streamwise vorticity were both strong. So the integration of that would also be strong. So, okay, the last thing I really want to get into here is looking a bit more at the mesoscale processes that are going on in the warm sector. And so really, if you look at this structure here, this is at 1445 UTC, so a couple hours, I guess, before supercells start to develop. And you have this really interesting, I guess, cloud shield or cloud evolution. You can see that there's this really distinct cloud band here, which I've labeled the leading cloud band, this really sharp band, that if you go into the Gulf of Mexico is actually associated with this long-lived boar and soliton, which was really cool. And I was really into that, even though that's not what I'm supposed to be looking at, but it was fun to look at. But you also have this secondary cloud band here, and this is actually the area that's the most important, and these are where the supercells are gonna form. So basically, behind this sort of secondary cloud band, you can see that your cumulus field is starting to develop, and that's really what becomes a supercell outbreak. But what led to the generation of these cloud bands, and were they significant, and if so, what was their significance? Just for fun, here's a tale of 2 super outbreaks. So on the top, I have the 1974 super outbreak, and on the bottom, I have the case I'm interested in. You can see that the cloud patterns are actually very similar looking. And there was actually this sort of cloud band that these satellite images were taken from Steve Corfidi's 2010 paper, but I think in this paper, he labeled it a cloud arc as he tracked it, but you can see that sort of cloud arc band is actually pretty similar to this leading cloud band, or it looks similar to the leading cloud band that I analyzed in this case. But overall, it's fairly similar looking. The main difference, I think, is that the warm sector was a lot more expansive in the 1974 outbreak. But otherwise, yeah, I thought it was pretty striking to see the two next to each other. So I guess sort of the final part of my dissertation and what is not currently published is really looking at and trying to understand these mesoscale processes that are actually going on in the warm sector and really how the cold frontal loft is leading to this development of convection in the warm sector, because I showed that there was a cold frontal loft moving into the warm sector, but it didn't really, I guess, seem super clear as how that's actually leading to convection initiation. So here's sort of the evolution of these cloud bands as they move through the southeast during the morning and early afternoon. And on the bottom, I'm showing ASOS observations from 3 different sites, and these are shown here with the stars in this left panel. And what you see is that as this sharp leading cloud band actually moved into the southeast, this was associated with this mesoscale pressure ridge You can see this here, if you can see my cursor, and also here. And so you are getting, it's probably due to adiabatic lifting, basically. You're getting cooling aloft that's responsible for that. And so you're getting this pressure rise at the surface on the mesoscale that lasted about an hour. And then that was actually followed by this clear band here that actually becomes more diffuse with time. And if you look, that's actually associated with what looks like a solitary wave of depression. And you can see that there is a wind shift associated with that feature in these two features as they passed over. But more interesting and more pertinent to what's actually going on in terms of convection initiation is this sort of mesoscale pressure ridge that I see in all three of these mediograms following the passage of this, or I guess basically associated with the passage of this trailing cloud band and the developing cumulus field behind that. So that's one thing I was like, oh, I thought we're supposed to see, rapid pressure falls or whatever, and I'm looking at these and I'm like, what is going on here? So essentially what I think is happening and what I will show with the model, with model simulations, is that this is due to a mesoscale region of basically adiabatic ascent, deeper moisture that extends, say, 100 or 200 kilometers out ahead of that cold frontal loft. And this is, I guess, ultimately what's responsible for this pressure rise. It's basically due to cooling aloft. So to look more at these bands and the structures going on here, the rock was not sufficient, so Glenn Romine actually ran this ensemble for me, and I used it for a couple different purposes, but one of which was to look at these mesoscale processes. And so not to get into the nitty-gritty details here, but what's important is that this is on a 3-kilometer domain, and that's what I'll be showing here. So there were 50 members that I was looking at. There were some limitations to these runs. Specifically, I guess, the southernmost Boeing segment of the first QLCS didn't persist, and it also struggled with the timing and location of QLCS2. But a lot of different forecasts did this. It wasn't just this ensemble. So that's, I guess you could think of that, could be important for the thermodynamic environment over the southeast later on because you don't have the cold pools like you did in reality. But I think the most important thing to keep in mind when looking at these for what's going on over the warm sector is that CI was actually a little bit too early and a little bit too far east in these. All the members, though, evolved very, very similarly. There are obviously mesoscale differences, but really the evolution in all of them was pretty much the same. So I'm going to show primarily the ensemble mean from all these. So it'd be the 50-member ensemble mean. And like I said, due to the low spread, you can see pretty distinct features in the ensemble mean, actually. So what I'm showing here is a cross-section animation that extends from the Texas Panhandle into the Gulf of Mexico. So this is basically not over the Outbreak region, but this is going over the Gulf of Mexico, and this is depicting the evolution of the Pacific cold front and the development of a cold frontal loft. And what you can see here out ahead of that is basically this moist layer that's capped by actually a very strong inversion in this region. It's basically getting shoved by, like a snowplow, kind of by this air mass. But at the surface, especially as you move over the water, you don't have, diurnal heating or anything heating the surface. And so you don't have a surface temperature drop associated with the passage of this. You see a wind shift, but you don't see any change in the surface thermodynamics. And so what happens is this air mass at very low levels, but not at the surface itself, is actually flowing over the Gulf of Mexico. And this is responsible for that long-lived bore that I showed you earlier. This is cool and all, and I think this is awesome because you can really see things very clearly if you're looking in this region, because things don't get messed up by diurnal heating over the Gulf of Mexico. So once you start to get into the southeast where you have a diurnal cycle, it gets a little more difficult to track things. So I think one thing that I've really taken away from this project is that if you are struggling to track something, oftentimes if you just kind of extrapolate, you may be able to see more signatures in the cloud field over the Gulf of Mexico as these things actually move into the southeast. Another thing to mention is that the low-level cold air, if you look at the evolution of a dry conveyor belt, is actually going to subside and be closer to the surface on the southern side of that cold front than it would be over the southeast as it moves over the warm sector. So that's another thing to keep in mind. But if we look at the same evolution, now looking from the southern Texas Panhandle into southwestern Alabama, you see that you have this downslope moving cold front, and it's basically this deep tropospheric cold air mass. But it encounters this deeper moist layer, but that's still stable because you have an elevated inversion. And what happens is you get the development of a cold front aloft. You also get deepening of this moist layer, pretty considerable deepening. And you can see you have this sort of dome structure here. It's probably easier to see in this plot that isn't moving. But this is out ahead of this cold frontal loft. So you can see that this white is basically the ensemble mean reflectivity, I think, equal to 0 dBz. So basically where these cloud bands are forming in all the members. And you have this mesoscale region of deeper moisture and sustained descent out ahead of the cold frontal loft, but definitely out ahead of the surface front. And that is actually associated with these rapid jumps in the inversion height. So basically what happens is you get these sort of elevated bore-like features that propagate on this capping inversion, and they rapidly lift that inversion to basically rapidly cool the mid-troposphere. And so this deepened moist layer extends more than 150 kilometers ahead of the cold frontal loft and then contains this mesoscale cloud and reflectivity band. So what is the relationship between the prefrontal dome of deeper moisture and the features observed over the warm sector, and how important are these disturbances to the destabilization of the warm sector? So here I'm showing the SEN for the most unstable parcel at 10, 12, and 14Z. So this is during the morning. The first 2 times are before sunrise. And on the right is the 1 hour most unstable SEN change in the ensemble mean. And you can see that the passage of each of these disturbances is rapidly decreasing the SEN by over 100 joules per kilogram. And these decreases are sustained. And this is, again, before any influence of solar heating. So once you do have solar heating, so by 14Z, you've already had this mesoscale destabilization, and then it's really fast to just, continually, or I guess, erode the rest of the SEN, deepen your boundary layer, warm the surface, further increase CAPE, but then you're not gonna have to wait until the evening to get convection initiation. So this is basically what's going on and how you're rapidly destabilizing this area after 2 convective systems move through in advance of basically this cold frontal loft. And so you can see that this bore A is what I have labeled here, is out quite far ahead of these cloud bands, which are the purple contours, and here is the reflectivity from the ensemble mean. So this is where the convection is actually, or the precipitation in the model is actually starting to develop, and this is actually quite far ahead. But remember, these are actually forming in an elevated inversion layer. This is not a surface-based inversion layer. So looking into this a little bit further, I found that there were actually 2 prefrontal disturbances that were generated, I guess, ahead of the system that moved in the southeast. The second one, which I'm calling elevated bore B, you can see the 1 hour potential temperature change here. This is located at the leading edge of that sort of mesoscale area, I guess, of really deeper moisture, sort of this pressure dome or mesoscale dome, I guess is how I've been calling it. But you can see that the passage of both of them basically leads to this sort of 2-part destabilization. But ultimately, you get sustained deepening of the low-level moist layer, cooling throughout the lower to middle troposphere, and weakening of the capping inversion, and so basically rapid destabilization. And so at 13Z, the low-level moist layer was potentially unstable, but you also had relative humidity values in the ensemble mean that exceeded 97.5% over a broad area above the boundary layer. And I will show in the next slide the soundings that correspond to this, but ultimately what happens is you get this MAUL, basically MAUL feature layer that forms above the unsaturated boundary layer. And so you end up with this sort of dual structure boundary layer that develops over the southeast, but was still topped by this remnant mid-level inversion. So what does this look like in the soundings? So here are the soundings from 4 points across this cross-section at 3 times. So the lightest sounding here would be the earliest time, and the darkest would be the latest. And so, for example, here you can see that in the first, or the top left, the boundary layer is topped by this overlying MAUL that deepens with time, while the overlying inversion is lifted and weakens. But in panel C here, which corresponds to this point that was initially ahead of the first disturbance and then was passed by that between 13 and 15Z, your most unstable SEN decreased by 102 joules per kilogram. But you don't really have a whole lot of a response down here in the surface. There was some very subtle moistening and some heating, but not a lot. This is primarily due to that mid-level cooling and the lifting of the capping inversion. And so you see a similar evolution here at point D, where you have these rapid SEN decreases. And so ultimately what happens is you have this growing sort of boundary layer that's sort of the combination of the MAUL that's on top of the unsaturated boundary layer. And as this remains capped, you're not getting deep convection initiation, but you're actually getting these sort of agitated cumulus bands that are forming over the warm sector. And so the character of these disturbances evolve throughout the morning, especially once you start to get turbulent mixing, and they become a lot more discrete and kind of change character, but their consequences persisted. You have this area that's been rapidly destabilized ahead of the front. So one thing I hypothesized was that this resultant increase in potential instability after sunrise is then going to invigorate basically this entire boundary layer. So you're going to basically strengthen the surface boundary layer, but also this MAUL that's above it, promote stronger convective overturning and deeper convective overturning. And so over time, these bands are going to deepen and perhaps lead to convection initiation. Here I'm showing some of the individual ensemble members depicting this evolution. So this is the reflectivity from two of them, and then the cross sections through these bands through the two members. And you can see that you have these sort of longitudinal-like reflectivity bands that develop in the ensemble members. And they have this structure that kind of resembles a longitudinal roll circulation, or kind of like a horizontal convective roll, except the spacing of these are quite a bit larger than you would see or expect to see with a traditional HCR. And so the spacing I actually was seeing in these model simulations, which again had a 3-kilometer grid spacing, was on the order of 20 to 30 kilometers, and that's much greater than you even order, say, magnitude 10 or whatever, greater than what you would typically see. And it's worth mentioning that George Bryan also documented these sort of circulations developing in a MAUL in a simulation of an MCS, although I believe that he was also finding these to be on the scale of around 3 kilometers. So, but you see this, in these different model, in the different ensemble members, and ultimately what happens is some of these updrafts eventually are able to overcome the mid-level capping inversion that has been weakened but still there, and leads to deep convection initiation. So that's, again, ahead of the cold frontal loft. So this is in this deepened moisture region, basically, this mesoscale region that has been lifted out ahead of that front. So I guess sort of to summarize, is that the formation of the MAUL alone was not sufficient condition for deep convection initiation because you still have that inversion. So what happens is you get this widespread region of agitated cumulus that remains capped, and once these updrafts can get strong enough and break through that inversion is when you get convection initiation in the warm sector. So just to kind of introduce some ongoing work, and I say ongoing, but it's really just getting started, but I've been working with Rich to sort of try to basically emulate or reproduce these structures in CM1 simulations. So ultimately, I'd like to really understand the characteristics and dynamics of these bands, but in reality, the environment was highly complex. There's a lot of multiscale process interactions going on to the warm sector evolution. So if you really wanted to capture the full evolution, you would need to depict the cold frontal loft, impinging on that low-level moist layer, the generation of this elevated bore, the sustained lifting, and then the development of the banded structures in this PBL MAUL layer, and then ultimately deep convection initiation. So can we simplify this down to something that's tractable and can be evaluated with CM1, and will similar evolution occur in this simplified framework? I guess to sort of summarize, I think we can so far, but keep in mind, we're not going to have any of this broader synoptic scale forcing, any of this sustained low-level moisture evacuation that's happening in reality. You can't depict the subsidence and downward momentum transport behind the cold frontal loft, so all of these things are not going to be captured. So we've started out, like I said, this is kind of the beginning, so this is all very subject to change and we're still refining things. But right now we're working with the 2D configuration analogous to a dam break. And so, for example, I'm basing this off of this cross-section from the ensemble mean. I'm trying to start out with a sounding that depicts the environment before any of these disturbances move through to see if I can get them to basically destabilize the environment as much as happened in reality and then lead to convection initiation. Spoiler, that's a lot more difficult than I would think. So this is, like I said, all subject to change. But basically, I've set up this to be like a dam break where this perturbation on the left-hand side is derived from the thermodynamic profile at the leftmost point here. I think that I'll probably have to find one that's a little bit farther in the cold air mass. But for now, that's what I've been doing. And I also, just to sort of play around with that and see how the perturbation amplitude affects the response. I've also subtracted 1 and 2 Kelvin off of that, just basically this whole profile to get a stronger cold air mass. But the consequence of that is this also changes the sign of the horizontal gradient near the surface. So that's something to keep in mind. But just to kind of show you what we're at. So this is 3 simulations that I've run. And this is what happens depending on the magnitude of the perturbation. The one thing I think that really sticks out here is the structure of the front is not right. So basically, in reality, you have a catafront structure, you have a cold front aloft, and so your front relative winds are moving from the cold air into the warm air. In these simulations, especially on the bottom panel, you see more of an anafront structure, but you also have more of a surface-based front here because the temperature perturbations because I've added or subtracted 2, it's reversed the sign of the temperature perturbations. But you can also see that you get a lot more lifting. You do get a MAUL, so this is relative humidity above 97.5 and 99.5%, and you have this mesoscale region of deeper moisture and lift out ahead of that. So far, I think we're on the right track, but I definitely welcome any suggestions that anyone may have on how to improve that. One thing I did want to mention is in this deepest lifting simulations with the coldest perturbation, the average spacing of these convective elements I'm seeing is roughly 10 kilometers. So they are tending to, the spacing is tending to increase as the lifting increases. That's definitely clear here, but still not quite the lifting and the structure that we want to see. So here is my summary and conclusions. And I'll take any questions.
Okay, paper's open. The talk is open for questions.
Really awesome talk, Manda. I was curious, so with the new CM1 runs, have you noticed, I know it's early, but have you noticed, like, anecdotally, any tipping points you found with all those interactions? Like, do you kind of find that there's this point of, accidental CI, no CI, or anything of that nature yet, or?
So we so far have not gotten CI. Okay. This is very, very, very preliminary. I think right now we're really trying to, what I'm trying to figure out anyway is, what sounding to use. Ideally, you would use this sounding and get the response of the whole evolution. I don't know if that will be practical. I will back up. We started out doing 3D simulations with a sounding that had already been lifted to see if these longitudinal sort of bands would develop with surface heat fluxes. The one issue, or not, I don't know if it's an issue, but the surface heat fluxes, at least under those bands, aren't actually that strong. And so if I'm putting in surface heat fluxes that are not, reflected of the real atmosphere, I do get convection initiation, absolutely. But we kind of stepped away from that and are taking this 2D approach, and I don't know the answer to that question, but hopefully soon. Like I said, we're really trying to dig into the 2D, so.
Great talk, Manda. One of the key things that you're presenting is this general area of lifting in the warm sector ahead of the front, the synoptic front. How do you distinguish between Bohr-type lifting versus maybe just frontogenetical lifting the whole air mass as the system is moving east?
That's a good question. I think in this case, the lifting I saw was so abrupt that it was associated with a discontinuity, and it propagated as a Bohr did, so out ahead of it. But I think that's a good question because let me see if I can find a good depiction here. So you can see that the cooling associated with the leading edge of this is so dramatic. There's like a 2-step sort of abrupt lifting. And again, this is in the ensemble mean, not each member. So it would be more amplified if you looked at an individual member. But that's a good question. Yeah, I think it would have to be, the amplitude of that disturbance and the amplitude of what's generating that and the character of, the thermodynamic character, but also the shear profiles that are leading to this wave generation, but also the propagation of that disturbance.
maybe coming back to Carrie's talk, like what you show here, like this is Carrie, I think Carrie Emanuel talked about hail events further north, but what you show is the moisture sources seem to be really coming from the Gulf. So did you see any evidence for soil moisture atmosphere interactions here? Not really.
No, I think the southeast is really unique in that it's so close to the Gulf and that you just have that replenishment of moisture, and it's so cloudy often there in these events. So no, but I think the other thing that Carrie mentioned was the importance of multiple diurnal cycles, and you definitely wouldn't see that this close to the Gulf. So, but thanks.
Further questions, comments? Otherwise, we can continue the discussion with the refreshments out here. Please join us. Manda, thanks again.